Hi everyone. Our next unit is the topic on radicals, and we're going to take a look at square roots, cubed roots, fourth roots, etc. But let's go back to square roots. All right, for extra credit, I gave this problem here, and I wanted you to try to solve it. It would be a good idea to use a calculator and then try to prove your result algebraically. And what's interesting about this square root is that we have nested square roots. The square root of 42 plus, and then the square root of 42 plus, etc., etc. Okay, well, while you're thinking about that, let's just review a little bit on radicals. Now, you've learned this last year in the 7th grade. Square root of 2, square root of 3, square root of 5, etc. These are examples of irrational numbers. And an irrational number is a number that's either the square root of a non-perfect square. For instance, the square root of 4 is 2. That's a perfect square. So it's either the square root of a non-perfect square or an infinite non-repeating decimal. All right, now let's just go over some terminology. This is the square root symbol, as you all know, and whatever is underneath the square root is called a radical, and it's understood to be an index of 2, but it's not written. It's usually over here. The index is written around here, but if it's not written, it's understood to be 2. And the expression underneath the radical sign is called the radicand. All right, now, if we take a look at this function on Desmos, which I'll leave up to you, you will see that the graph of y equals the square root of x, well, if we pick some values, when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is root 2, whatever that decimal approximation is. 3, root 3, etc., etc. Notice we cannot pick negative numbers. X has to be positive because if, or equal to 0, because if x is negative, we have an imaginary number and we want to deal with a set of real numbers. What this graph looks like is the following. On Desmos, y equals the square root of x looks like this. Notice that it's always above the x-axis, and we cannot pick anything on the negative side, and the answer is never, never negative. When we're given the square root of a number, it has to be positive. If we wanted our answer to be negative, let's say the square root of 4, we negate it by putting a negative sign outside. So the graph of y equals the opposite of the square root of x would give us this branch. Together, these two branches make one equation, which is y squared equals x, which is a sideways parabola. But that's just a note. I just wanted to emphasize that if we want a square root to be negative, the negative must be outside. All right, so that's our review. Now, the properties of square roots I believed you learned last year. And that is that when we have the square root of a times the square root of b, that could be simplified to the square root of a times b, and vice versa. And we use this rule to simplify square roots. The other rule that we may use is that the square root of a over the square root of b, where b is not equal to 0, can be written as the square root of a over b. So if we have a square root of a fraction, we could always split it up into the square root of the numerator divided by the square root of the denominator. All right, that's just a side note. Now, how do we use these rules? Well, it all depends on when a radical expression is simplified. So I'm going to show you some radical expressions that I was planning to put on in the do now if I were to teach this in class, and radical expressions that are not simplified. And I'd like you to take a minute and come up with 3 conditions for a radical to be simplified. Okay, these are considered to be simplified. 5 times the square root of 3. 6 over the square root of 5 divided by 7. And root 5 minus root 7 divided by 2. These are simplified. Now here are 3 that are not simplified. Actually 4 I'll give you. The square root of 45. The square root of 1/5. 6 over the square root of 2. And finally, 14 over 3 plus radical 2. So take a minute, pause the video, and look at these 4 carefully. What conditions must be satisfied for a radical expression to be simplified? Okay, so pause and we'll get back to it. Well, a radical expression is not simplified, well, is simplified, I should say. In the first case, the radicand cannot have a perfect square factor. So 45 has a perfect square factor, and that is 9. So that's not considered simplified. Also, there cannot be a fraction in the radicand, like in this one. Thirdly, there cannot be a square root in the denominator, like this one, because the denominator is irrational. And how can we take an infinite non-repeating decimal and divide it into a whole number? We can't. How many places will we carry the decimal point in the divisor? We don't know. We would have 1.414 ... into 6. We would have to carry this decimal over to make it a whole number, but there are infinitely many places. And then finally, this is the same reason. This is a binomial denominator, but we notice that the binomial denominator has an irrational number as well, so it's not simplified. So let's write these 3 conditions on the next page. The other problem I have, 6 over radical again, is 14. So copy this into your notes. A radical is simplified when these 3 conditions are satisfied. 1, the radicand does not contain a perfect square factor other than 1. So perfect squares, well, we just square consecutive numbers. 2 squared, 3 squared, 4 squared, 5 squared. These are perfect squares. All right. Secondly, the radicand does not have a fraction. And thirdly, the denominator of the fraction, the denominator of a fraction does not have a radical. So let's revisit the ones that are not simplified and see how we can simplify them. So let's take the square root of 45. The square root of 45 can be written as the product of a perfect square, which is the square root of 9, and 5. And using that product property that we discussed before, since 45 is 9 times 5, we can write this, and that simplifies to 3 root 5. So 3 root 5 would be the simplest form for the square root of 45. In the second one, which was the square root of 1/5, I believe, we could use that quotient rule and separate the square root of the numerator and the denominator. But this becomes 1 over radical 5. So now we don't satisfy condition number 3. So what we do in that case is we use what's called rationalize the denominator. And to rationalize the denominator, we multiply the top and bottom by a square root that will make the denominator a whole number. And what would that be? How about the square root of 5 over the square root of 5? That's perfect. Notice that we are not changing the value. We are just multiplying by 1, which is the multiplicative identity. So this simply becomes the square root of 5 over 25, the square root of 25, which is just the square root of 5 over 5. So you'll know that when we multiply square root of 5 by square root of 5, the answer is just 5. And that's our simplest answer in simplest form. Okay, now the same could be done for 2. So let's look at that. 6 over radical 2. Well, we would multiply that by radical 2 over radical 2, which gives us 6 square root of 2 over 2, and that simplifies into 3 root 2. That takes care of that one. When the denominator is a binomial, however, things get a little tricky. And the one I gave you, let me just take over 3 plus radical 2. Now, to rationalize the denominator here, we can't just multiply by the square root of 2 over the square root of 2, because we would have to distribute and we would have a 3 square root of 2 in the denominator. So that doesn't work. So we go back to a very important property that we discussed, the difference of 2 squares, which you know is a squared minus b squared. So to rationalize this binomial denominator, we will multiply the top and bottom by 3 minus root 2 over 3 minus root 2, so that when we square the 3 and we square the 2, they will become the square root of 2. The square of the square root of 2 is 2, and we will have a whole number. So therefore, this is also 1. And we've got 14. Now do not distribute the numerator. Leave it that way. Just use the difference of 2 squares in the denominator. So that gives me 3 squared minus root 2 squared. So that leaves me with 14 times 3 minus radical 2 over 9 minus 2, which yields 14 times 3 minus radical 2 over 7, which divides through into 2 times 3 minus radical 2. So notice that when we did not distribute the 14 in the numerator, it was good because we ended up dividing through with the denominator. These are called conjugate pairs. And this is a very, very powerful property of conjugate pairs. When we multiply them, we square the first, we square the second, and subtract. And this is perfect when we have square roots. Okay, so that takes care of the simplification. Now I'd like you to try one by yourselves. I'd like you all to simplify this one. Okay, I wasn't sure what number I'm up to. Number 4. Okay, that's in red, wrong color. Okay, I'd like you to simplify 12 times the square root of 2/3 minus 2 times the square root of 1 1/2 plus the square root of 54. Okay, that's one. Another one is the square root of 2 times 8 times the square root of 2 minus 2 times the square root of 8 minus 3 times the square root of 32. The next one is square root of 90 plus the square root of 160 divided by the square root of 2. All right, so copy these down, pause the video, and then restart once you're done. I've written out the solutions for you. In number 4, I split up the first one, the square root of 2/3, into the square root of 2 over the square root of 3, rationalized the denominator, multiplied the numerators, got the 3 in the denominator, and this simplifies to 4 square root of 6. In this second part, I rewrote 1 1/2 as the square root of 3/2, separated the fraction, rationalized the denominator, and obtained 2 square root of 6 over 2, which divides through to square root of 6. And the square root of 54 can be simplified into 3 square root of 6. These are like radicals. Like radicals, think of the square root of 6 as an x, and we could combine like terms. So we keep the common radical, and we add the coefficients. 4 and 1 is 5, and 3 is 8. So the answer is 8 times the square root of 6. Number 5 can be done in various ways. The approach that was done here is that I simplified within the parentheses. 8 times the square root of 2 is already simplified. I simplified the square root of 8 as in the square root of 4 times the square root of 2 and multiplied and obtained 4 square root of 2 here. The square root of 32 is the square root of 16 times the square root of 2 and multiplied 3 by 4 and got 12 square root of 2. Combined the like radicals in the parentheses and obtained negative 8 times the square root of 2. And then multiplied. And since multiplication is commutative and associative, I could put the negative 8 in the front, the square roots of 2 together, and get the negative 8 times the square root of 4, which is 2, and that answers negative 16. It's interesting that it comes out to be an integer. You could also distribute if you'd like, and then simplify the resulting radicals in a similar way, but you should get negative 16. And then for number 6, there are lots of ways to do this. One way is to simplify the numerator by factoring out the square root of 9 and the square root of 16. I get a common radical of 10. And then combine the like radicals and then divide through using that division property. Another way to do this, which may be easier, is to rewrite this as the square root of 90 divided by the square root of 2 plus the square root of 160 divided by the square root of 2. Use that quotient property, and because 2 divides evenly into 90 and 160, we could bring it into the radicand. We get the square root of 45 plus the square root of 80. Okay, wait, oops, I made a mistake. I put too many plus signs. Yes, and then simplify from there. So this becomes 3 square root of 5 plus 4 square root of 5, which gives us the 7 square root of 5 if we simplify each. We could factor out a square root of 9 on this one and a square root of 16 out of that one. Okay, so that is how we simplify. Let's take a look at a few more. Back. Okay, we're up to number 7. Wait, let me just... Okay, so what I wanted to show you are these. I wanted to show you binomial radicals, binomial denominators in the radical. So let's simplify 3 minus the square root of 5 divided by 2 plus 3 times the square root of 5. Okay, that's one. And one for an extra challenge is this one. 1 over 1 plus root 3 minus radical 5. Here, we notice that the denominator has 3 terms. Okay, try these, think about them, and replay the video so we could go over it. All right, so let's take a look at these solutions. For number 7, I multiplied by the conjugate 2 minus 3 radical 5 over itself. And in the numerators, I did say to leave it in factored form. But here, because the radical 5, we have 2 binomials, I would say, it would be good to just multiply them out as if we FOIL the first, outer, inner, and last. And keep in mind that the negative root 5 times the negative 3 root 5 multiply to 15 times, multiply to positive 3 times 5, so that this combines to be 21 minus 11 root 5. That would be the numerator. The denominator, we square the first, we square the second, and remember the exponent rule. When we square up factors, we move this exponent inside the parentheses. So we square the 9, we square the square root of 5, which is 5, and we end up with the following answer. 21 minus 11 times the square root of 5 over 41. Number 8 is a trickier problem, because now I would like to use that conjugate rule. So what we do is we group the first 2 terms together. Let's call it A. So our problem becomes 1 over A minus root 5. So to rationalize the denominator here, we multiply by the conjugate, and we're left with A plus root 5 over A squared minus 5, using the A squared minus B squared property. And now we put A back. So A was 1 plus square root of 3 plus square root of 5. And A squared I have here. This part's over here. We square the binomial and we FOIL. So the first gives us 1. The last gives us 3. And the inner and outer each give us root 3. So it's 2 root 3. And that simplifies to 4 plus 2 root 3. And we write that here for A squared minus 5. And we combine and we get negative 1 plus 2 times the square root of 3. Now we rationalize the denominator again by multiplying by the conjugate. And notice I left the numerator in factored form. I mean, we can multiply it out as a trinomial times a binomial, but I will not bother here. What I'm concerned about is rationalizing the denominator and simplifying this as much as we can. So when we square negative 1, we get 1. And we square 2 root 3, we get 4 times 3, which is 12. So that combines to negative 11, and this is our answer. Okay, so that's just about it with radicals that I wanted to go over with you. And I will be assigning this through the homework for practice. I don't think we'll find problems like number 8, but when I want to give one to you, I will write it up in the homework. All right, have a great rest of the day. Bye.